Welcome back. Problem 5.99. This problem is taken from chapter number 5, Analysis and Design of Beam for Bending, and the book name is Mechanics of Material by Beer and Johnson, 6th edition. And the topic is singularity function or Macaulay's method. So statement of the problem is using singularity function, write the equation defining the shear and bending moment for the beam and loading shown, and in B part use the equation obtained for moment to determine the bending moment at point C, and check your answer by drawing the free body diagram of entire beam. So you can see this is a cantilever beam having fixed support at point C, and there is a distributed load from A to B, and that is magnitude W naught. So you have to find the shear and bending moment equation by using singularity function. So let's start with the solution. So as you know that we have this table that is shown over here for bending moment and shear force diagram by using singularity function, and in this diagram we can locate that this is the diagram for distributed load, and from here you can see the distributed load start from here till the end. Clear? But here this is starting from the point A and till point B, so we have to make it till the end. So what we will do is that we will proceed it further, and we will add this W naught through entire length of the beam, and then we will subtract it the same downwards in order to cancel its effect. This is W naught. Now we will apply this singularity function. So you can see this is the equation for this distributed load, which is W of x, and that is equal to, for this entire W naught, you can see here A is equal to 0 because it is starting from point A. So this equation will be equal to W naught into x minus A is 0, so x power 0. Now for this distributed load, you can see that this distance from A to B is small a. So what we will do is that we will write minus, why minus? Because this load is upward and here this load is downward. So for downward this is positive and for upward it is negative. So I will write W naught into x minus A power 0. So we will get this W is equal to W naught minus x power 0 is 1. So minus W naught into x minus A power 0. And we know that this W, we know that dV over dx is equal to minus W. So from here this W will be equal to minus dV over dx. So we will put the value of W. W is equal to W naught minus W naught into x minus A power 0. So what we will get is that if I take dV is equal to minus W naught minus W naught into x minus A power 0 into dx. And if we integrate it on both sides, so we will get shear force will be equal to minus W naught x, and that will be equal to plus W naught into x minus A power 1, which will be the shear equation. This is equation number 1. Also, we know that dm over dx is equal to shear force. So from here, this shear force into dx will be equal to dm. So I will write dm is equal to, this shear force equation is minus W naught into x plus W naught into x minus A power 1, and dx is there. So if you integrate it on both sides, so you will get the equation of moment that will be minus W naught x square divided by 2 plus W naught into x minus A power 2 divided by 2. Clear? And this will be the equation of moment. This is one method you can get the equation of shear force and bending moment. Second thing is that you can use this diagrams or graphs in order to get the shear force equation and bending moment equation. So let's use it as well. We will see, we will get the same answer. Now here you can see shear force equation is this one. So for the loading that is shown about for W naught, so it will be equal to minus W naught into x minus A. A is 0, so x minus 0 power 1 plus, now this load is upward, clear? So for that it will be plus for upward, plus value for upward. So I will take W naught into x minus A power 1. So what we will get is minus W naught x plus W naught into x minus A power 1. So you can see this is the, okay, this is the equation. You can compare it with the equation 1. You can compare this equation and this equation, both are same. Similarly, you can also find moment equation. So moment equation is this one, clear? So for this uniformly distributed load of W naught, so I can write minus 1 over 2 W naught into x minus A. A is 0, so x square plus 1 over 2 y plus, because this W naught is upward now. So it will be plus into x minus A power 2. So you can see this is the equation. This equation and this equation both are same. So you can try any of the methods. So this was our first part. We use singularity function in order to define the shear force equation, clear? And then bending moment equation, which is this one. Now we will move towards second part, and in second part use the equation obtained for M to determine the bending moment at point C. So what is C? C is here. So here x is equal to 2a. So put, this is your part B. Put x is equal to 2a in equation 2. So we will get this M is equal to minus W naught 2a square divided by 2 plus W naught into 2a minus a whole square divided by 2. So it will be minus W naught 4a square over 2, and that will be equal to W naught a square over 2. So moment will be equal to minus 2 W naught a square plus W naught a square over 2. So if you take the LCM, that will be 2 and there is 1. So divide 2 by 1 is 2 and multiply it with minus 2. So minus 4 W naught a square plus 2 divided by 2 is 1, multiply by W naught into a square will be W naught a square. Okay, if you further simplify it, it will be equal to minus 3 W naught a square over 2. This is the equation of the moment, clear? And that is the answer. Now the last part is that it has been given that check your answer by drawing the free body diagram of an entire beam. So what we will do is that we will draw the free body diagram of entire beam. So there is a distributed load from point A till point B, clear? And that is given as W naught. This is point A, this is point B, this is distance A, and from B to C the distance is also A. So when you remove the fixed support at point C, this is C, so you will be having a vertical reaction that is equal to RC, as well as you will have a moment MC, clear? And there will be a horizontal reaction force as well, but that is equal to 0 because there is no horizontal component. So we will write sum of all forces along x direction must be equal to 0 and force toward right side is taken as positive. So RCX will be equal to 0. It means that RC is equal to RCX, horizontal component, is equal to 0. The second thing is that we will apply another equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So this is distributed load when converted into point load. So it will be W naught and it will be multiplied by the length over which it acts, and it acts at a distance of A by 2 from either side. Now we will apply this equation. So we have one force minus W naught into A, which is acting downward, and other force is plus RCY, so is equal to 0. So from here we will get RCY will be equal to W naught into A. And the last thing is that you will apply the equation of equilibrium, that is sum of all movement about point C is equal to 0 and taking the counterclockwise movement as positive. So here you can see one movement is clockwise, that is minus MC, and the second movement about point C is this W naught into perpendicular distance is, this is 3A divided by 2, because A plus A by 2 is equal to 3A divided by 2, and this is producing counterclockwise movement, so it will be positive. So I can write plus W naught into A into 3A divided by 2 is equal to 0. So movement about point C will be equal to 3W naught A square over 2. Okay, so this is the movement at point C by using equation of equilibrium and from the free body diagram of the beam. So you can see here this is positive, so it means our resumed direction is correct. And from this shear bending moment equation using singularity function, here when you put it the value of x, so you are getting this minus 3W naught into A. So this means that this is correct. Why? Because negative means if you remove this, so moment will be equal to 3W naught A square over 2, and that means this is clockwise direction. So you can see from this and this we are getting the same answer and same direction. So this is all about this problem 5-99. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 5-100. This problem is taken from chapter number 5, Analysis and Design of Beam for Bending, and book name is Mechanics of Material by Beer and Johnson, 6th edition. The topic is singularity function or Macaulay's method. So statement is using singularity function, write the equation defining the shear and bending moment for the beam and loading shown. And in part B, use the equation obtained for M to determine the bending moment at point C, and check your answer by drawing the free body diagram of entire beam. So you can see this is a cantilever beam having fixed support at point C, and there is a distributed load which is triangular load from A to B having magnitude W naught. Clear? So we have to determine the shear force equation and bending moment equation by using singularity function. So let's start with the solution. As we can see that we have this table, basic load and corresponding shear and bending moment expressed in term of singularity function. So from here you can see this figure having distributed linear load. Clear? And this is starting from A. So its distributed load Wx will be equal to K into x minus A power 1, where K is the slope of this graph. So this is starting from this point and ending at this point, but here you can see it is starting from point A and end at point B. So what we will do is that we will project it till point C in order to add till point C. So this is what we have, what we are going to do. We are going to add this with this. Clear? Okay. Now here you can see this load is seem to be distributed load W naught. So what we are going to do is that we will add this distributed load like this in upward direction, clear, as well as there is a triangular load. So here it is W naught, so here it will be 2W naught. So we will also add it in downward direction, and it will be upward. So what we did is that we added this portion over here in downward direction, and then we added this portion in upward direction so that it cancel each other. Here it is W naught because we have added here W naught. This is W naught, here it is 2W naught. So here it is W naught. So what we are going to do is that we will apply the singularity function for this graph. For this one, you can see we will find K, and K1, this will be equal to K1, and K1 will be a slope. Slope is perpendicular or hypotenuse base. So perpendicular is 2W naught and base is 2 times of A. So K1 will be equal to W naught by A. Similarly for this, we have K2, and K2 will be also equal to perpendicular is this one for triangular load, and base is A. Now we can apply this equation. W of x is equal to, first for this one, for this case here, A is equal to 0 because it is starting from point A. Clear? So we will use this equation. So W will be equal to K1 into x minus 0 power 1. Okay, this was the first one, triangular load. Now here you can see we have a distributed load in upward direction, clear. So for distributed load we have this this is the equation. So W is downward, so this is positive, so here I will write negative because here the load W naught is upward. So minus W naught into x minus A power 0 because A is this one. And the last thing is this triangular load again. Since this is upward, so I will write minus K into x minus A power 1. So I will write minus K2 into x minus A power 1. Now you can put the value of K1. So K1 is W naught divided by A, x minus W naught into x minus A power 0, and K2 is also minus W naught over A into x minus A power 1. As we know that dV over dx is equal to minus W, so from here we will get W is equal to minus dV over dx. So dV will be equal to minus W times dx. So Wx is this one. So dV will be equal to minus W naught by A into x minus W naught into x minus A power 0 minus W naught over A into x minus A power 1 into dx. So if we integrate it on both sides, we will get the shear force that will be equal to minus W naught x square over 2A plus W naught into x minus A power 1 plus W naught over A into x minus A power 2 divided by 2. So this is the shear force equation. Now we know that dm over dx is equal to V. So dm will be equal to V into dx. So I will write it, dm is equal to V is minus W naught x square over 2A plus W naught into x minus A power 1 plus W naught over 2A into x minus A power 2 into dx. So if you integrate it, you will get the moment, and moment will be minus W naught x cube over 6A plus W naught into x minus A power 2 divided by 2 plus W naught into x minus a power 3 divided by 6a. So this is the shear force equation and this is the bending moment equation. You can also find it by using this table. Clear? So let's try it. So V is equal to, for this triangular load, this one, this whole one. So you can see we can write K is equal to W naught by A into X minus A power 1. So here A is equal to 0. So I will write X power 1. Now for this distributed load, that is upward, so distributed load, the shear V equation is this one, not this. This is the W1. So let me correct it. K over 2. K is W naught over A, and that is 2. That is minus. Clear? And X minus A. So X A is equal to 0. So X square. For distributed load, this is the equation. So minus. So since our load is upward, here you can see. So I will write plus W into X minus A power 1. And then there is a triangular load of this, that is upward. So again we will use this equation. So minus K into X, sorry, not this equation. This is the equation. Minus K is for, so for upward it is K by 2. So we know that K is again W naught over A. K2 is W naught over A. So W naught over 2A into X minus A power 2. So you can compare these two equations. You can see that both equations are same. Similarly, you can find the moment equation here. So for distributed load of this one, this is the first one, the moment equation is this one. Minus K, K is W naught over A multiplied by 6, because this is 6 into X minus A. A is equal to 0, so I will write X cube. The second one is for distributed load. So for distributed load, it will be plus, because here the distributed load is downwards and here it is upward. So I will write plus 1 over 2 W naught into X minus A power 2. And then there is a triangular load upward. So we will use this minus K, which is W naught over A times 6 into X minus A power 3. You can compare these two equations. Both are same. So whatever method you use, you will get the same shear force and bending moment equation. Now in second part, it is given that to find the moment at point C. So at C, X is equal to 2A. So what we will do is that put X is equal to 2A in equation of moment. So I will put it, moment will be equal to minus W naught. X is replaced with 2A whole cube divided by 6A plus W naught over 2 into 2A minus A power square plus W naught into 2A minus A. This is A power 3 divided by 6A. Okay, so if you simplify it, moment will be equal to minus W naught multiplied by 8A cube over 6A plus W naught over 2 into A square plus W naught into A cube divided by 6A. So this will be minus 8 W naught A square over 6 plus W naught A square over 2 plus W naught A square over 6. Now you have to take the LCM. So 6, it will be minus 8 W naught A square plus 3 W naught A square plus W naught A square. So this moment will be equal to minus 4 W naught A square over 6, or that is equal to minus 2 W naught A square 3. and you can also write it 2 over 3 W naught A square, and the moment is clockwise. Clear? Now in last portion, check your answer by drawing the free body diagram of entire beam. So for that I will copy it and we will move toward next page. Let me paste it over here. So you can see when you remove this support at point C, so you will be having a reaction force which is RCY. You will be having a horizontal reaction force RCX, and you will be having a moment MC. Now this is a triangular load, so when converted into a point load, it will be equal to 1 over 2 W naught, and the length is A, and that will act at a distance of A by 3 from this side. Clear? So now apply the equation of equilibrium that sum of all moment about point C is equal to 0, taking the counterclockwise moment as positive. So about point C, one moment is minus MC, which is the reaction moment, and the second moment about point C is this load into perpendicular distance is this one, and this is producing counterclockwise moment. So A by 3 plus A will give you 4A by 3. We will write plus 1 over 2 W naught into A into 4A by 3 is equal to 0. So moment about point C will be equal to 4 W naught A square over 6A, or that is equal to 2 W naught A square over 3. This is not 6A, this is only 6. So what we obtain from this is MC is equal to 2 W naught A square over 3, which you can see is positive value. It means that your assumed direction clockwise is correct. Now you can compare this with this value. Both are same. So it means that we have found the correct equation of shear force and bending moment equation. And this was all about problem 5-100. I hope you have enjoyed this video and you are liking and learning it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 5.101. This problem is taken from chapter number 5, Analysis and Design of Beam for Bending, and book name is Mechanics of Material by Beer Johnson, 6th edition. And the topic is singularity function or Macaulay's method. So statement of the problem is using singularity function, write the equation defining the shear and bending moment for the beam and loading shown. And in part B, use the equation obtained for bending moment M to determine the bending moment at point E, and check your answer by drawing the free body diagram of the portion of the beam to the right of E. So you can see this is overhanging beam having pin support at point A and a roller support at point C. And there is a distributed load, uniformly distributed load from B to D having magnitude W naught. So the total length of the beam is 4 times A. Clear? So what we have to find is that using singularity function, we will write its shear and bending moment equation, and then bending moment equation, we will find the bending moment at point E. So for x is equal to 3a, we will find the bending moment, and then at the end drawing the free body diagram of portion beam right to the E. So this is the right side of the point E. So we will find this bending moment by using the section at the right side. So let's start with the solution. So first step is that if you remove this pin support at point A, so you will be having reaction force, let this is A, and if you remove this roller support, so you will be having reaction C. So we'll find this A and C by using equation of equilibrium. And what if you convert this uniformly distributed load into point load? So it will be W times the length over which it acts, and the length, this is the length 3A. You can see this is 3A. So I will write it W into 3A. and that will act at a distance of a by 2 from this side. A by 2. Okay, this is the distance. Now we can apply the equation of equilibrium. So first equation of equilibrium is that sum of all moment about point C is equal to 0, taking the counterclockwise movement as positive. So about point C, the first movement is this A force and perpendicular distance is 2A and it is producing clockwise movement. So I will take it as negative. So I will write A multiplied by 2A and that is negative. The second moment that is produced about point C is this W naught into 3A and perpendicular distance is A by 2. And this is also producing clockwise, so it is also negative. So I will write minus 3 W naught into A by 2 is equal to 0. The sum of all moment about point C is equal to 0. So I will write 2A into small a is equal to minus 3 W naught A square over 2. So what if I need A? So I will divide 2A on both sides. So minus 3 W naught A square and it will become equal to 4A. So we will get minus 3 W naught A over 2. A over 4, sorry. 4. 4. So what I get is A is equal to minus 3 W naught A over 4. This is the reaction force offered by pin support at A on this beam. Now we'll find this Cy by using another equation of equilibrium, that is sum of all moment about point A is equal to 0 and taking the counterclockwise moment as positive. So about point A, the first moment is this due to this force C and perpendicular distance is 2A and this is producing counterclockwise movement, so it is positive. So we can write C multiplied by 2A. The second moment is produced due to this W naught into 3A force, and now the perpendicular distance is 2A plus A by 2, which is equal to 5A by 2. Clear? So I will write, this is producing clockwise, so I will write 3 W naught into A into 5A divided by 2. Because you can see A plus A by 2, we take LCM, so 2A plus 2A plus A is equal to 5A divided by 2. So this total distance from this point till this point, this is 5A over 2. Okay. Now their sum of all moment about point A is equal to 0. So I need C. So 2AC is equal to 3 into 5 is 15. So I can write minus 15 plus 15 into W naught A square over 2. So it will give us from this we will get this C will be equal to 15 W naught A square over 4A, and that we will get C is equal to 15 W naught A square, sorry, A will cut and we will left with this one. So this is the reaction force offered by pin roller support at this beam. Now we will use this table in order to find the shear force and bending moment using singularity function. So here we have calculated A is minus 3 W naught A divided by 4 and C is equal to 15 W naught A over 4. Okay, so starting from the shear force diagram, so I will write V of X is equal to the first load starting from this left side hand side and moving toward right side. So first load is A, clear. So for point load, the figure is this, and for that shear force equation is this one. Since load is downward and it is at a distance of A, and here the load is upward and A is equal to 0. So we can write it as, for downward load it is minus P. So here I will write, instead of P we have load A into X minus A is equal to 0. So it will be AX naught. Okay, the second load is, you can see, is uniformly distributed load and it is at a distance of A. So for uniformly distributed load, the shear force equation is this one, and this is downward, so it is minus W naught into, so I will write minus W naught into X minus A because it is at a distance of A from point A. And the third load is this C load. You can see this is a point load and it is upward, so we will again use this equation. So it will be plus C into, it is now acting at a distance of 2A from the A point. So I will write X minus 2A power 0. Okay, and this, for distributed load, this power is 1. You can put the value of A, so A is equal to minus 3 W naught into A divided by 4, clear? And since X is equal to 0 at A, so 0 power 0 is 1. And minus W naught is same W naught into X minus A power 1 plus C, and C value is 15 W naught A divided by 4 into X minus 2A power 0. So this is your shear force equation. Now we'll find the bending moment equation, and for that we will again start from point A. So you can see this is point A having point load. So for point load, the bending moment equation is this one. For the downward load, here the load is upward. You can see the load is upward. So I will write plus A into X minus A, which is 0. So X minus 0 power 1. And for distributed load of W naught, it will be, you can see the this is the equation for distributed load. So I can write, this is downward is negative, so I can write minus 1 over 2 W naught into X minus A, because this is acting at a distance of A from point A, power 2. And the last one is C, which is acting at a distance of 2A. So again, for point load, I will go to this. So minus C, it will be plus C because the load is upward. So plus C into X minus A power 1. And you can see this C is at a distance of 2A. So correct it. This is 2A. Okay, now put the value of A. So A is minus 3 W naught A divided by 4 into X, because X minus 0, so X is 1, clear? And the second one is, this will become minus 1 over 2 W naught into X minus A power 2, and putting the value of C, which is 15 W naught A divided by 4 into X minus 2A power 1. And that is the required bending moment equation for the beam. Clear? Now we have solved our part first, which was using singularity function find the, this was part A. Using singularity function we have calculated or find out the shear force equation as well as bending moment equation. Now in part B we have been asked that use the equation obtained for M to determine the bending moment at point E. So you can see that this point E is at a distance of X is equal to 3A. So what we will do is that put X is equal to 3A in equation, for example, let this is equation number 1. So put X is equal to 3 in equation 1. So you will get moment is equal to minus 3 W naught A into 3A, clear, divide by 4 minus 1 over 2 W naught. X will be replaced with 3A, so 3A minus A power 2 plus 15 W naught a over 4 into 3a minus 2a power 1. So we will get minus 9 w naught a square over 4, and from here we will get 2a square, so which will be 4a square. So 4 w naught a square divided by 2, and from here we will get 15 w naught. Here we will get a, so a into a is a square over 4. This is moment m of x. And when you solve this it further, you can take the LCM. So 4 will be LCM, so it will be minus 9 w naught a square minus 4 w naught a square plus 15 w naught a square. So what we will get is moment will be equal to 9 minus 3 is minus 13 plus 15. So it will give you minus 2 w naught a square over 4. So it means that moment will be equal to minus 1 over 2 w naught into a square. This is the value of moment at point E. Now what we will do is that in the last portion we have been asked you check your answer by drawing the free body diagram of the portion of beam to the right. So what we will do is that we will cut the beam and at a distance of A from this side D, clear, and we will find the moment at this point E. So let me draw it. This is the beam, clear. This is your point D, this is your point E, where there is a distributed load acting downward, and this distance is given as A. And when you cut it, you will be having a shear force V and you will be having moment M. So we will find this moment E at point E. So how they'll find this moment? So we will use the equation of equilibrium, that sum of all moment about point E is equal to 0, taking the counterclockwise moment as positive. So this was distributed load W naught. So when converted it to point load, it will be equal to W naught into the length over which it acts, so A. And it will act at a distance of A by 2 from either side. Clear? Now we'll apply equation of equilibrium, that sum of all forces about point E is equal to 0. So you can see one moment is clockwise, which is external reaction moment, that is clockwise, so it will be negative, and the second moment about point E is this, which is W naught into A into distance A by 2, and it is also clockwise, so it will be negative. So I can write minus W naught into A divided by 2 is equal to 0. So it means that moment about point E is equal to W naught A square over 2 minus, and again you can see it is minus 1 over 2 W naught A square. And you can compare it with the moment about point E that is obtained from moment equation from using singularity function. So it is minus 1 over 2 W naught into A square. You can check it, clear. And this is also minus 1 over 2 W naught A square. So this was all about this problem 5.101. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 5.102. This problem is taken from chapter number 5, Analysis and Design of Beam for Bending, and book name is Mechanics of Material by Beer and Johnson, 6th edition. And the topic that we are covering is singularity function, or it is also known as Macaulay's method. So statement is, using singularity function, write the equation defining the shear and bending moment for the beam and loading shown. And in part B, use the equation obtained for M to determine the bending moment at point E, and check your answer by drawing the free body diagram of the portion of the beam to the right of the E. So you can see this is the beam simply supported beam that is having pin support at A and roller support at point D. At point B we have a point load, and at point C we have another point load that is having magnitude P. So by using singularity function, we have to write the shear and bending moment equation for the beam, and then in part B, the equation that we obtain from for the bending moment, we have to put the value at for the point E and to obtain the moment, and then we will verify our answer by drawing the right side of the point E free body diagram and finding the moment. So let's start with the solution. So first step is that if you remove this pin support at point A, so you will be having vertical reaction. Let this is AY, and if you remove this roller support, so you will be having reaction force which is known as dy. We will find this ay and dy by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point D is equal to 0, taking the counterclockwise movement as positive. So about point D, first movement is due to this ay into perpendicular distance is this 4a, and this is producing clockwise movement, so it will be negative. So I will write ay multiply by 4a, and that is negative. The second moment is due to this P load, and that is perpendicular distance is 3a, and this is producing counterclockwise movement, so it will be positive. So I will write plus P times 3a. And the last fourth that is producing moment about point D is this P, and perpendicular distance is 2a, and it is also producing counterclockwise movement, so it will be positive. So plus P into 2a, and the sum of all this moment about point D will be equal to 0. So it means that 4a ay is equal to 5pa, and you can get this ay will be equal to 5 by 4p. Clear? And if you solve this, you will get 1.25 times p. So this is the vertical reaction of the pin support on the beam. Now we will find this dy by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So ay is upward, which is 1.25 p, minus this p and minus this p. So minus 2p is plus this dy is equal to 0. So from here, when you get 1.25 minus 2p will give you minus 0.75. So dy will be equal to 0.75 times p. Now you have these reaction forces, so we will use singularity function in order to determine the shear and bending moment equation. So let's define it. So here we have this reaction force which is 1.25 p, and this reaction force was 0.75 p. Okay, so let's proceed further and we'll determine the shear force equation. So shear force equation V of x. So here you can see we will start from this left hand side and we will move toward right hand side. Clear? And at the end we will neglect this 0.75 p, because we will see that the effect of it will be 0. We will include, and I will show you why we are neglecting it. So V of x. So starting from first 1.25. So you can see this is the load shown on the beam, and that is starting at a distance of a. So its shear force equation is this one, minus p. Here the load is upward, so I will write this load 1.25, because it is upward, so it will be taken as positive 1.25 into x minus a. So here this is starting at point a, starting point, so here a is equal to 0, so I will write x power 0. The second load is this p, and this is downward, so I will write minus, we'll use again this equation, minus p into x minus a power 0. Clear? And the third force is this p also again, so minus p into x minus, now here this is acting at a distance of 2a from point a, so I will write x minus 2a power 0. And the last force which we will neglect, but I will show here that it will be having no effect. So plus 0.75 times P into x minus, now it is acting at a distance of 4a. So you can see this is 4a. So I will write x minus 4a. Now what if you take x is less or equal to 4a? So when you put it in this equation, so if the x is less than 4a, so this term will be negative, and anything inside this negative in this bracket, which is also known as Macaulay bracket, so it will be considered 0. So either x is less than 4a or equal to 4a, this term will be 0. That's why we will take neglect this. So shear force V of x will be equal to 1.25 times P, 1.25 times P, and x is start, so 0, so and 0 power or anything power 0 is 0, 1. So minus the second one is P into x minus a power 0 minus P into x minus 2a power 0. So this is equation number 1, and that is the shear force equation. Now what we will do is that we will find the moment equation. So m of x will be equal to, here again for the point load, the moment graph is given as that. So starting for this first point, our load of 1.25, so the load is downward here, so this is negative. So for the upward load it will be positive. So plus P, which is 1.25 times P into x minus a. So a is again here 0 for this 1.25 P load, so x power 1. The second load is this minus P, so minus P into x minus a power 1. And the last load is 1.25, so minus P into x minus 2a, because it is acting at a distance of 2a from this point A, and it will be having power 1, and we will neglect the last term because it will give us the 0 value. So what we do is that we will write it, m of x is 1.25 times P into x minus P into x minus a power 1 minus P into x minus 2a power 1. And this is equation number 2, which is the bending moment equation. So in first part we have find out the shear force as well as bending moment equation. Now what we will do is that we will go to the part 2, and in part 2 it is given that use the equation obtained for m to determine the bending moment equation at point E. So this is point E. So point E is at a distance of x is equal to 3a. So what we will do is that at x is equal to 3a, put in equation number 2. So this moment about E will become equal to 1.25 times P multiplied by 3A minus P times 3A minus A power 1 minus P into 3A minus 2A power 1. So it will give us uh, 3.75 PA minus 2 PA and minus P into A. So when you solve this, this is minus, these two are minus 3P plus 3.75P. So it will give you 0.75 P into A. So this will be the moment at point E. And that is the answer of our second part. Now in third part, we have been asked to check your answer by drawing the free body diagram of the portion of the beam to the right of E. So what we will do is that we will cut the beam over here and we will draw the free body diagram, because we have been given to determine the moment when taking the right side of the E. Clear? So let me cut it over here. So when I cut it at a distance of A and draw the free body diagram, so this will be the free body diagram. This is your point D, where you have a load of 0.75 P. Clear? And this is distance of A. So when you cut it, you will be having a shear force V, and you will be having a moment M E, because this is point E. Now you can apply the equation of equilibrium, that sum of all moment about point E is equal to 0, and taking the counterclockwise moment as positive. So about point E, one is moment is minus ME, because this is clockwise. Another moment is due to 0.75 into perpendicular distance is A, and this is producing counterclockwise movement, so it will be positive. So 0.75 times P into A is equal to 0. So it means that moment about point E is equal to 0.75 times PA, which is, now you can compare this moment which is obtained from the equation, and this is the moment which is taking the section to the right side of the E. Both are same. So hence it is verified that our required equation of shear force and bending moment is correct. And that was all about this problem 5.102. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 5.103. This problem is taken from chapter number 5, Analysis and Design of Beam for Bending, and book name is Mechanics of Material by Beer and Johnson, 6th edition. And the topic is Singularity Function or Macaulay's Method. So statement of the problem is, in part A, we have been asked, using singularity functions, write the equation defining the shear and bending moment for the beam and loading shown. And in part B, use the equation obtained for M to determine the bending moment at point E, and check your answer by drawing the free body diagram of the portion of the beam to the right of E. So you can see this is a simply supported beam having pin support at A and a roller support at D, and their distributed load from A to B having magnitude W naught, and from B to E having magnitude 2W naught, and then from E to D it is W naught. So what we will do is that we will find the equation of shear and bending moment by using singularity function. So let's start with our first solution of first part. So what if we remove this support at point A? So you will be having reaction force. Let this is represented as RA. And what if you remove this roller support at point D? So you will be having a reaction force, and this is equal to RD. And we will find this RA and RD by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So you can see W naught which is acting over here, and when we convert this W naught into a point load, so it will be equal to W naught into the length over which it acts, which is A, and this will act at a distance of A by 2 from either E point or D point. So I will write A over 2. Now this W naught when converted into point load, so it will be equal to 2W naught into the over length over which it acts, which is 2A. So I will write 2A, and that will act at a distance of A from point E. Clear? And the last load, which is W naught, this one which when converted into point load, so it will be equal to W naught into A, and the distance this from point B, from mid till point B, is A by 2. Now you can see the distance from this point load and point A will be equal to 7A by 2. Why 7A by 2? Because you can see this is A plus A, and this is A, and this is A by 2. So it will give you 7A by 2. And now we will apply sum of all moment about point A is equal to 0. So starting from this load, RD into perpendicular distance is 4A about point A, and it is producing counterclockwise movement, so it will be positive. So I will write 4 times A multiply by this RD. Clear? And the second moment is due to this load W naught into A, and perpendicular distance is 7a by 2 and it is producing clockwise movement, so it will be negative. So I will write minus W naught into A into 7a over 2. The another moment of this load about point A is this load multiplied by perpendicular distance is 2 and this is also clockwise, so it will be negative. So I will write minus, this will be 4W naught into A into perpendicular distance is 2A. And the last force which is producing moment about point A is W naught into A and perpendicular distance is A by 2 and this will be also clockwise. So I will write minus W naught into A divided by 2 is equal to 0. So we will get 4RD multiplied by A minus 7W naught A square over 2 minus AW naught A square, and this will be minus W naught A square over 2 is equal to 0. So it means that 4RD into A is equal to 7W naught A square over 2 plus 8W naught A square over 1 minus plus W naught A square over 2. So what if I take LCM? So this is 2. So this will be 7W naught A square plus 8W naught A square plus W naught A square. And that will give you 7 and 8, 15 plus this is 16. 7, 8, 15 plus 16. 16 divided by 2 is 8. Okay, I think I have made mistake. Okay, this is 7 into W naught. Okay, this there is 1, so this will be 16 because 2 divided by 1 is 2 and 2 into 8 is 16. So made this correction. Now 16 and 7 is 23 plus 1, 24. So correct it. This will be 24 W naught A square over 2, which is equal to 12 W naught A square, and that is equal to 4RD multiplied by A. So what we will get if you divide 4A on both sides, so you will get RD will be equal to 3W naught into A. So this is the reaction force of this roller support on the beam. Now we'll find this RA by using equation of equilibrium, that sum of all forces along y direction is equal to 0 and upward force is taken as positive. So we do not have R. So RA minus this W naught into A minus this 4 times W naught into A and this minus W naught into A plus this RD, which is plus 3W naught into A is equal to 0. So you can see this will be minus 4 minus 1 minus 5 minus 6. So minus 6W naught into A plus 3W naught into A will give you RA will be equal to minus 3W naught into A is equal to 0. So from here you will get RA will be equal to 3W naught into A. So now we have reaction on both sides. So what we are doing is that we will represent it over here. So you can see this is 3W naught into A and this is also 3W naught into A. Since we have distributed load on the beam, clear? So what we will do, go to this figure and you can see you have distributed load that is acting at a distance of A. So shear force equation will be this one. But this distributed load is starting from this and it is going towards the end. And here you can see this is this portion and it is up to this portion and this portion. So we will make it as per our diagram. So what we will do is that if I make it as a horizontal, because all this will be W naught. So this will be your one load. So this now this remaining this portion will be also W naught. Clear? So we will cut it. This will be also W naught. And what if I make it toward this side? Clear? If I add this much load, W naught. So on lower side, I will make the same, but in above direction. Clear? This will be W naught. In order to cancel effect, you can see this and this effect will cancel, and we will only left with this same portion. Now we can apply this figure for finding the shear force and bending moment diagram. So first we will find V of X, shear force equation. Starting from left hand side and moving toward right hand side, we will neglect the last force, which is 3W naught into A, because you have seen that in previous problem I have shown that the effect of this force becomes 0 when X is less than 4A or equal to 4A. So you can try it yourself. So starting from this point load, so first load is this point load. This is the figure of point load that is acting downward. So shear force equation is this one. So for here, this load is upward, so it will be positive P. So P here is 3W naught into A and X minus A. A is equal to 0 because this load is starting from point A. So this is 0. Now the second load is this W naught, which is acting throughout the length. Clear? Let me show you. It is acting throughout the length. Clear? So we will use this equation, W minus W naught into X minus A. A is equal to 0 for this load. So I will write minus W naught into X power 1. Okay, the another load is this W naught, which is acting. So I will write minus W naught into X minus. Now you can see this load is acting at a distance of A from this point A. So W naught into X minus A power 1. And the last load is this one, which is upward. So this load, you can see this is negative for the downward, and this load is upward. So W naught will be positive. So I will write plus W naught into X minus. Now this load is acting at a distance of 3A from this point A. So I will write X minus 3A power 1. To further simplify it, this shear force equation will be equal to 3W naught A x power 0 is 1. So minus W naught x1 minus W naught into X minus A power 1 plus W naught into X minus 3A power 1. So this is your shear force equation. Now we'll find the bending moment equation. So for bending moment equation, M of X will be equal to, again starting from this left side, for this 3 low point load. So bending moment equation is this one. Since this is downward force and this is negative, so for upward force it will be positive. So plus P, and P is 3W naught into A into X minus A. A is equal to 0 because it is starting from point A. So power 1. The second load is this W naught. Clear? And we will write the W naught equation is this one. Okay, so that will be equal to minus 1 over 2 W naught into X minus A power 2, and A is this distance. Clear? The third load is this W naught for the length of 3A. So I will write minus 1 over 2. Let me correct it. Minus 1 over 2 into W naught into X minus X minus 3A 3A power 2. We have left this one, okay, because for A here it is equal to 0. So minus 1 over 2 W naught into X square. Let me explain. The first term is for this. Clear? This term is for this portion, and this term is for this portion, and the fourth term is for this portion. Okay, now if you simplify this, so you will get this M of X will be equal to 3W naught AX This term will be equal to minus 1 over 2 W naught x square. This term will be equal to minus 1 over 2 W naught into x minus a square plus, okay, for this load, this is upward, so this will be plus. So plus 1 over 2 W naught into x minus 3a whole square. And this is, let's say, equation number 2. So this is the equation of shear force, and this is the equation of bending moment for the beam and loading shown. So now our next part is that what use the equation obtained for M to determine bending moment at point E. So we have to find the bending moment at point E. So E is at a distance of 3a from point A. So we will put x is equal to 3a in equation 2. So when you put x is equal to 3a, so it will be equal to 3w naught a into 3a minus 1 over 2 w naught into 3a whole square minus 1 over 2 w naught into 3a minus a power square plus 1 over 2 w naught into 3a minus 3a whole square. So this term will become 0, and we will left with moment m of x will be equal to 9 w naught a square minus 9 by 2 w naught a square minus 1 over 2 w naught into 2a, 3a minus a is 2a, so 4a square. Okay, so if you take LCM, so it will be give you 2, so 9w naught, okay, 2 divided by 1 divided by 2 is 2, 2 into 9 is 18. So 18w naught a square minus 9w naught a square minus 4w naught a square. So it will give us 9, and minus 4 is minus 13 plus 18 is 5w naught a square over 2. This is moment about point E. So I will write moment about point E will be equal to 5w naught a square over 2. And this is the answer of our second part. Now in third part, we have been asked to check your answer by drawing the free body diagram of the portion of the beam to the right of E. So to the right of E, if you take this section and draw the free body diagram, you will get this moment ME, and we will compare it. So what we will do is that we will section it over here and draw the free body diagram. So let me move toward this page. So this is the beam. Okay, this is your point D where you have 3w naught into A, and there is a distributed load acting on it which is equal to w naught. This length is A. Clear? So when you cut it, you will be having a shear force V. This is point E, so it will be VE, and you will be having a moment ME. So we'll find this moment by using equation of equilibrium, that sum of all moment about point E is equal to 0, taking the counterclockwise moment as positive. So when this W naught load is converted into point load, it will be W naught into A, and that will act at a distance of A by 2 from either side. Now you can apply the equation. So about point E, one moment is ME, which is clockwise. So I will write minus ME. The second moment is due to this load into perpendicular distance is A by 2, and this is also clockwise. So it will be, sorry. Okay, this will be clockwise. So it will be also negative. So I will write minus W naught into A divided by 2. And the another load which is producing moment about point E is this load into perpendicular distance A, and this is producing counterclockwise movement. So it will be positive. So I will write plus 3W naught A into A is equal to 0. So moment about point E will be equal to minus W naught A square over 2 plus 3W naught A square. So if you take the LCM, so it will be minus W naught A square plus 6W naught A square will be moment about point E. So moment about point E will be equal to 5W naught A square over 2. And you can see that this is the moment by cutting the beam and taking the right side of point E. Now you can compare it with this value that is obtained from the equation of bending moment. Both are same. It means that our required equation of shear force and bending moment is correct. So this was all about problem 5.103. I hope you have enjoyed this video and you have learned from this. Those who are new to my channel, then subscribe it and don't forget to press icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 5.104. This problem is taken from chapter number 5, Analysis and Design of Beam for Bending, and the book name is Mechanics of Material by Beer and Johnson, 6th edition. And the topic is still singularity function, or it is also known as Macaulay's method. So statement is using singularity function, write the equation for shear and bending moment for the beam ABC under the loading shown. And in part B, use the equation obtained for moment to determine the bending moment just to the right point of point B. So you can see this is the beam, clear, and having a point load at point A, which is P, and you have been asked to find the shear and bending moment equation for the beam. So let's start with the solution. So if you remove this fixed support at point C, so you will be having a reaction force CY, you will be having a horizontal reaction force CX, and you will be having a moment about point C which is equal to MC. So again, using a force couple system, if you move this point P load to the point B, so what you will do is that you can transfer it to this point, but you can see there is a perpendicular distance which is A, and it is producing moment which will be equal to MA in counterclockwise direction. So what you will do is that you will replace this with a moment that is equal to M multiplied by A. So we will draw the free body diagram for the beam which is shown in the diagram. So this is the beam and this is point B where you have a load of P by using force couple system, and you will having a moment in counterclockwise direction which is equal to P into A, and distance from this point which is point A till point B, this is point B, this is point A, is A, and distance from B to C is also A. And we have shown that there is a vertical reaction force CY as well as CX as well as moment MC. We are not interested to find out this MC, CX and CY because they will be not used, and the last term starting from this left hand side to the right hand side, this term on the right hand sides will be neglected, and you know that I have solved too many problem on that. Now what we will do is that you can see this is the figures for loading, this is for shear force, and this is bending moment. So starting from the left side from A to B, you can see there is no load, and at point B you have a load which is P that is acting downward. So you can see you will use this equation, this figure, that is minus P acting at a distance of A. So shear force equation will be this one. So I will write V of X is equal to minus P into X minus A power 0. And we have a moment as well as at this point which is PA, and you can see for moment acting at point A from the start, the shear force is 0. So there will be no term for the moment. So we will only get shear force equation will be equal to minus P into X minus A power 0. This is your equation number 1. Now moving for bending moment equation. Bending moment equation. I will write m of x. So again, for a load of P, you can see this is P that is acting downward. So the bending moment equation is this one. So I will write minus P into x minus a power 1, because this P is acting at a distance of a from point A. And we have a moment as well, which is PA. So due to the moment equation will be this one. So I will write minus this m naught will replace with PA. So PA into x minus a power 0. And we can say that this will be our equation number 2. So equation 1, and I will write equation 1 and 2. Equation 2 are required shear force and bending moment equations using singularity function. Now this is the answer of our first part. Now in second part, in B part, it is given that use the equation obtained for M to determine the bending just to the right point of point B. So this is point B. So just right to the point B. Here we will take x is equal to A and we will put it in equation number 2 in order to find the bending moment just to the right of the B. So put x is equal to A in equation number 2. So moment about that will be equal to moment about point B, that will be minus P into A minus A power 1. Clear? And minus P into A minus A power 0. So it will be equal to minus P into A minus A is 0, 0 power 1 minus PA into 0 power 0. So you can say 0 power 1 is 0. So it will be minus P into 0 is equal to 0. And that will be minus PA 0 power 0 is 1. So I will write it 1. That will be equal to moment at point B. So moment at point B will be equal to minus P times A. And that is the answer of our this question. Now this negative sign shows that moment at point B will be equal to P times A, and while representing this bending moment on beam or bending moment diagram, this will be counterclockwise movement, CCW, counterclockwise movement. And you can also see that movement at point B is again MA, which is counterclockwise here. So this is the answer of our second part. And that was all about this problem 5.104. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 5.105. This problem is taken from chapter number 5, Analysis and Design of Beams for Bending, and the book name is Mechanics of Material by Beer and Johnson, 6th edition. And the topic is Singularity Function or Macaulay's Method. So statement is in part A, we have been asked using Singularity Function, write the equation for shear and bending moment for the beam ABC under the loading shown. And in part B, use the equation obtained for M to determine the bending moment just to the right of point D. So you can see this is the beam having a point load at point C, and at this point we have P. Clear? Now due to this loading you have to find the shear force and bending moment equation using singularity function. So let's start with the solution. So when you solve this, and if you remove this fixed support at point B, you will be having a vertical reaction force By, you will be having a horizontal reaction force Bx, and you will be having a moment which is Mb. And what if you move this point P load to point A? So definitely you can move that by using force couple system, and you can see there is a perpendicular distance from point A till this, which is equal to P into L by 3, and it is producing clockwise movement. So I can write it, this movement will be equal to PL by 3. And similarly, if you move this point load to point D, so what you can do is that you can move it P, and there will be a perpendicular distance from P to D, which is L, and this is producing counterclockwise movement. So this PL over 3 will be counterclockwise. So again, I can write this as counterclockwise movement is like this. So you can see this will be also equal to PL divided by 3. Now we can draw a free body diagram for the beam shown below, or the one which I am drawing. So this is point B. You will be having a vertical reaction force By. You will be horizontal reaction force Bx, and you will be having a moment which will be Mb at point B. At point A, you can have this P load and a clockwise movement which will be PL divided by 3. And at point D, this is your point A, this is your point D. Again at point D you have a vertical load P, and you will have a counterclockwise movement which is PL divided by 3. The distance from A to D can be obtained if you have L by 3 and L by 3, so it will be 2L by 3. So I can write it over here, this is equal to 2L divided by 3, and from D to B this distance is L by 3. Now by using singularity function, we will start from the left hand side, clear, and we will move toward right hand side, and the term toward right hand side, the last terms By, Bx and Mb, they will not contribute in this equation, so we will neglect them. Why? I have explained it in so many problems. You can also try, at the end they will give you the zero value. So starting for the shear force equation using singularity function. So we know that singularity function is Vx. At this point, at point A, we have a load P. So due to this load, this P is acting downward. So this is the figures which is used for the low point load, since it is acting at point A. So the shear force equation is this one, but in this condition, A is equal to 0. So I will write Vx is equal to minus P into x minus 0 power 0. This is the shear force equation. Here A is equal to 0. Now at this point P, you can have this moment as well, which is PL over 3. So equation for the moment for the figure used for moment is this one, and shear force bending moment will be shear force is 0. So it is not producing any shear force. So this term will be 0. Now the second load is point P, and it is acting at a distance of 2L by 3. 2L, this distance is 2L by 3, which is equal to A for this point load. So I can write minus P into x minus A. A is 2L over 3 power 0. And this moment is also having no shear force equation. So this will be equal to V of x will be equal to minus P, and x power 0 is 1. So it will be minus P, and minus P into x minus 2L by 3. Let this is your equation number 1, which is the required shear force equation using singularity function. Now what I will do is that I will find bending moment equation using singularity function. And for that I can write it m of x starting for this load p. So bending moment equation will be this one. You can see bending moment for point load p is this one. So I will write minus p into x minus a for this p load is equal to 0. So I will write x square, not x square, x minus 0 power, this is 1. So correct it, this is 1. Okay, plus now this you have a clockwise movement which is equal to PL over 3. So for movement, the bending moment equation is this one. Since this is for counterclockwise movement, clear, and here this is clockwise, so I will write it plus. So plus m naught is PL over 3, clear. So PL over 3 into x minus 0, because a is equal to 0 for this movement. So it will be having power 0. You can check it over here. The third load is this point P, and this is downward. So minus P into x minus a for this is 2L over 3. So minus 2L by 3 power 1. And the last term for this movement will be PL over 3, and this is counterclockwise, so it will be minus m naught. So minus m naught is PL over 3. Over here you can see moment is PL over 3 into x minus a is 2L by 3 power 0. Okay, so what we can do is that we can simplify it. Moment about x is equal to minus p into x plus PL over 3, because x power 0 is 1, and this term will be minus p into x minus 2L over 3 power 1 minus p into L over 3 into x minus 2L by 3 power 0. This is your equation number 2 and is the required bending moment equation using singularity function. Now in part B, we have been asked use the equation obtained for M to determine the bending moment just to the right point of point D. So this is point D. So just try it at point D means that at x is equal to 2L by 3, we will find this moment. So put x is equal to 2L by 3 in equation number 2. So moment about point D will become equal to minus P, x will be replaced with 2L over 3 plus PL divided by 3 minus P times 2L divided by 3 minus 2L divided by 3 power 1 minus PL divided by 3 into 2L divided by 3 minus 2L divided by 3 power 0. So we will get minus 2PL over 3 plus PL over 3 minus P times this term will be 0. Anything power 0 power 1 is 0. So minus P into L divided by 3, and this term will be 0. 0 power 0 is 1. So we can write it minus 2PL divided by 3 plus PL divided by 3. This will be 0. Minus P into 0 is 0. And minus PL divided by 3. Okay. So you can see these two can cancel with each other. So that will be equal to moment about point D. So moment about point D will be equal to minus 2PL divided by 3. Or you can say that this moment is equal to minus, if you want to remove minus, so it will be P2PL divided by 3, and that will be counterclockwise. y is moment at point D. And this is the answer of our this question. And that was all about this problem 5.105. I hope you have enjoyed this video and you are learning as well. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 5.115. This problem is taken from chapter number 5, Analysis and Design of Beam for Bending, and the book name is Mechanics of Material by Beer and Johnson, 6th edition. And the topic that we are covering is singularity functions, or it is also known as Macaulay's method. So statement is a beam is being designed to be supported and loaded as shown using singularity function. Find the magnitude and location of maximum bending moment in the beam. And in part B, knowing that allowable normal stress for the steel to be used is 24 ksi, find the most economical wide flange shape that can be used. So you can see this is a simply supported beam with a pin support and roller support at both ends, and there is a distributed load of 3 kips per feet over a length of 15 feet, and there is a point load of 22.5 kips at a distance of 3 feet from point A. So you have to find the location, magnitude and location of maximum bending moment using singularity function, and then you have to choose the most economical wide flange shape. So let's start with the solution. So first step is that if you remove this pin support, so you will be having a vertical reaction force, let this is ay, and there is a horizontal reaction force which is equal to ax, and if you remove this roller support, so you will be having only vertical reaction, then let this is cy. So first we will find this by using equation of equilibrium. So what we will do is that we will convert this distributed load into point load. So when you convert this distributed load into points load, so you have to multiply this load 3 kips per feet with the total length, which is 12 plus 3, and that is equal to 15, and that is 75 kip. Clear? Now you can apply the equation of equilibrium. So we will apply equation of equilibrium that sum of all moment about point C is equal to 0, taking the counterclockwise moment as positive. So at this point C, the first moment is this 75, and perpendicular distance is this is half of 15, which is 7.5, and this is producing counterclockwise movement, so it will be positive. So I will write 75 multiplied by 7.5, 7.5, because it is acting at a distance of half of 15, which is 7.5 feet. And let me correct, is 3 multiplied by 15 is 45, not 75. So this is 45. Okay, the second moment that is produced due to this 22.5 kips load and perpendicular distance is 12 feet, and this is also producing counterclockwise movement, so it will be positive. So I will write plus 22.5 into perpendicular distance is 12. And the last load that is producing movement about point C is AY, and perpendicular distance is 15, and it is producing clockwise, so it will be negative. So minus 15 times AY. The sum of all moment about point C must be equal to 0. So when you solve this, you will get this AY will be equal to 40.5 kips. That is acting vertically upward. Now you can find AX by using equation of equilibrium that sum of all forces along X direction must be equal to 0, and force toward right side is taken as positive. So only there is a horizontal force AX, there is no other force, so it means that AX is equal to 0. Now we will find this RY by CY by using this equation of equilibrium. So you can see AY, which is upward, that is 40.5 minus this 22.5 kips load, 22.5 kips load minus 45 plus cy is equal to 0. So from here you will get cy will be equal to 27 kips. Okay, now you have all these reaction forces. So what we will do is that we will find shear force equation and bending moment equation by using singularity function. So for that you can see we have this table that is shown over here. I will show it in the book. This is the table that is basic load and corresponding shear and bending moment is expressed in term of singularity function. So what we are doing is that we are only using, we have point load and distributed load, so we are using these graphs for finding, and these are the equation: shear force and bending moment equation for point load and shear force and bending moment equation for distributed load. So I have copied over here. So let me show you here. You can see I will write shear force equation, shear force equation using singularity function. So starting from this left side, you can see we have vertical reaction force, which is AY, and you can see for the point load, the load is acting downward. So shear force equation is minus P into X minus A power 0, where A is this distance. So for this AY, we have A is equal to 0 and this load is upward. So I will write this V will be equal to AY, which is 40.5 into, this is the equation, x minus a. So a is equal to 0, so x power 0. Now we have this moving from here, we have 22.5 kips load and this is acting downward. So we will use this equation, but that p will be positive. So plus 22.5 into x minus, now a is here is 3 feet. So I will replace it with 3 and that is power 0. Okay. The other thing is that you can see you have a uniformly distributed load of 3 kips per feet. So this is the diagram and this is the shear force equation. So this distributed load start from at a distance of A, and the shear force equation is this one. The load is downward, so this is minus W. So here you can see this distributed load start from the start till the end. Clear? So A is equal to 0 for this. So I will write minus W is 3 kips per feet. So 3 into x minus 0 power 1. And the last term is cy. We will neglect it because we are starting from left side and moving toward, and always you have to neglect the last term because this will give you 0 if I include it. So I will write plus cy into x minus a. X minus a, and a is total 15 because this is acting at this point. So this is a. So that is 15 feet. So that is power 0. Again, you can see that for x is less than or equal to 15, this term will become 0 because anything that is negative inside this Macaulay bracket will be considered as 0. So if x is less than 15, this term will be 0, or x is equal to 15, this term will become 0. So we will neglect this. Let me remove this. That is only for your understanding purpose. Now we will going to find the bending moment equation. So bending moment equation using singularity function. Okay. So let me write it over here. So this bending moment equation will be equal to, now starting again from the left side, you have AY load. So the moment equation is this one. For this load is downward, this is negative. So I will write positive. So A is AY is 40.5 into x minus A. So for this AY load, A is equal to 0 because it is starting from the start. So this power 1. Now the second load is again 22.5. So I will write plus 22.5 into x minus A is 3 feet. So 3 power 1. The third load is distributed load, which is 3 kips per feet. So for distributed load, you can see the moment equation is this one. So minus 1 over 2 W naught is 3 into x minus A. So A is equal to 0. So x minus A power x minus 0 power 2. Okay. So we can write this equation as 40.5 x minus 3 over 2 into x square plus 22.5 into x minus 3 power 1. So this is equation number 1, which is for shear force, and this is for bending moment. Now in our first part, we have been asked to find the magnitude and location of maximum bending moment. So you have to find the maximum bending moment, and we know that maximum bending moment, I will write it, maximum bending moment occurs where shear force is equal to 0. So what we will do is that put uh, V is equal to 0 in equation 1. So we will see that this is 3 feet distance from point A to B. Clear? So for x is greater than 3 feet, x is greater than 3 feet and less than 15 feet. There is a point where the shear force will be equal to 0. Let this point is xd. So we will find it xd is greater than 3 feet and less than 15 feet. So maximum bending moment occur where shear force is equal to 0. So we'll put it in this equation, which is V is equal to 40.5, because x power 0 is 1, plus 22.5 into x minus 3 power 0 minus 3x. So we will put it V is equal to 0. So it will be equal to 40.5. This plus 22.5. This term will also be equal to 1 because anything power 0 is 1. So minus 3, we will replace this x with d because we are going to find the distance at which shear force is equal to 0. So from here 3xd is equal to 40.5 plus 22.5, and xd will be equal to, this is 40.5 plus 22.5 is 63. So 3 into xd is equal to 63. I think we have made any mistake. Let me check it over here. This is correct because the load is upward. This load is 22.5 is downward. So you can see this equation is minus p into x minus a power 0 for downward. So it should be negative. So let me correct it. This is negative. And this is also correct. So here we will also rectify, this is also negative because you can see this W is this 22.5 load is acting downward. So for downward we have minus P into x minus 1. Okay. So what we will do is that this will also negative. Okay. So this will be negative and this will be also negative. That will be equal to 18. So from here you will find the location of the point D, which is 6 feet from the start, and at this point at a distance of 6 feet there the shear force will be 0 and we will get the maximum bending moment. Now put xd is equal to 6 feet in equation 2. So we will get maximum bending moment that will be equal to 40.5. X will be replaced with xd 6 feet minus 3 over 2, 6 square plus 22.5 into x. 6 minus 3 is 3. Clear? So when you solve this, you will get the maximum bending moment will be equal to 1 to 1.5 kips into feet. And if you want to convert it into inch, so 121.5 into 12 will convert this kip into inch. So the value of maximum bending moment will be equal to 1458 kip into inch. So this is the answer of our first part. These two are the answer of our first part. Now we will move towards second part, and second part is that find the most economical wide flange that can be used. And we have been given allowable stress is 24 ksi. So let me write it. We have allowable stress is 24 ksi. We have maximum bending moment that we have calculated here is 1458 kip into inch, and we have to find most economical wide flange beam. Okay, so we know that allowable stress is equal to maximum bending moment divided by minimum section modulus. So from here we will get this minimum section modulus will be equal to maximum bending moment divided by allowable stress. So put the value of this maximum bending moment and allowable stress. So 1458 divided by 24 ksi. So 24, when you divide it, so you will get 60.75 cubic inch. So this is minimum section modulus. Now what we will do is that we will go to the table that is given at the end of book. I will show you at the end of book. You have to go to the wide flange beams property of rolled section, and then you have to choose the US customary. Clear? So let me choose a pen. Okay, so you can see this is the section modulus. So the value was 60.75. So that we will choose those beam which are near to 60.75. So one thing is that you can see this is nearest to 60. So W 21 into 44. 21 into 44. So I will write it. The first one is W 21 into 44 having section modulus is 81.6 cubic inch. This is section modulus. This is beam, W beam. So we have one option is this. Now we'll move toward another one. The second one is, you can see here is, this one is closer. I think there is a problem. Okay, you can choose it. I will write some of the values which you can see. 18 by 50, it will have 88.9 cubic inch. The third one is W 16 by 40, that is 64.7 cubic inch. The fourth one is W 14 multiplied by 43 having section modulus 62.6 cubic inch. The fifth is W 12 into 50, that is having 64.2. The sixth is W 10 into 68 having 75.7 cubic inch. In this way, you can have many options for selecting wide flange beam, but we have been asked to find the most economical wide flange beam. So you can see the most nearest value is this one. Clear? This is the most nearest. But in this W 14 into 43, this is pounds per feet. This is the weight of this beam, pound in 14 pounds per feet. So we have to select a lesser weight, and among all these options, so you can see this W 16 into 40 is having smallest weight per feet, and its section modulus is 60.4, which is also greater than the minimum section modulus. So what we will choose? We will choose W 16 by 40 is the economical wide flange beam for the loading shown and allowable normal stress is 24 ksi. So this is the answer of our question. And that was all about this problem 5.115. I hope you like that and you have learned it. Always remember that while solving this problem, you have to be very careful, because a small mistake can put you in trouble. If you have any question, you can ask me in comment section, and if you have any uh, problem related to the singularity function, you can tell me. I will share you the link of that lecture that I have explained in detail, and you will definitely find it interesting and knowledgeable. Again, thank you so much for subscribing my channel and liking me.